Welcome to Cambridge IGCSE Physics, Lesson 62.1, Galaxies. Today we explore the vast collections of stars that make up our universe, including our own Milky Way galaxy. Let's examine our learning objectives for today. By the end of this lesson, you will be able to, first, state that galaxies are made of many billions of stars. This means understanding the enormous scale of stellar collections. Second, know that the Sun is a star in the Milky Way galaxy. This places our solar system in cosmic context. Third, know that other stars in the Milky Way are much further than the Sun from Earth. This demonstrates the vast distances within our galaxy. These objectives align with Assessment Objective 1, which tests scientific knowledge and understanding. Now let's define our key vocabulary. Each term is essential for understanding this lesson. First, galaxy, which means a massive collection of billions of stars held together by gravitational force. These are the largest structures of stars in the universe. Second, Milky Way, which means our home galaxy containing our solar system and all stars visible to the naked eye. This is where Earth and our Sun are located. Third, billions, which means thousands of millions. In scientific notation, 1 billion equals 1 times 10 to the power of 9. Understanding these terms precisely is crucial for grasping the enormous scale of cosmic structures. Let's explore our first core concept. What are galaxies? The fundamental principle states that galaxies are enormous collections of stars held together by gravity. This means that gravitational force keeps billions of stars organized in a single structure. The definition is, a galaxy contains many billions of stars bound together by gravitational attraction. Each galaxy is like a stellar city containing vast numbers of individual stars. The scale is enormous. A typical galaxy contains 100 billion to 1 trillion stars. That's 1 times 10 to the power of 9 up to 1 times 10 to the power of 12 stars. To understand this scale, 1 billion equals 1,000 million, or 1 followed by 9 zeros. The diagram illustrates galaxy structure with spiral arms containing billions of individual stars and a central bulge where stars are most concentrated. Notice how the stars are organized in a rotating disk structure. This principle is fundamental because it explains how matter organizes on the largest scales in the universe. Now we examine our home galaxy, the Milky Way. This is where our solar system is located. The Milky Way is a spiral galaxy with rotating arms of stars. Its structure includes spiral arms that rotate around a central core. The size is enormous, approximately 100,000 light-years in diameter. A light-year is the distance light travels in 1 year, about 9 trillion kilometers. The Milky Way contains about 200 billion stars, written as 2 times 10 to the power of 11. Our Sun is located in an outer spiral arm, not at the center. The diagram shows 2 views. The side view reveals the flat disk structure with a central bulge where most stars concentrate. The Sun appears as a small dot in the outer region. The top view shows the spiral arm pattern with the Sun's position marked. Notice how the Sun is far from the galactic center, in what astronomers call the Orion arm of our galaxy. Let's work through our first example about galactic scale. The problem states, if the Milky Way contains 2 times 10 to the power of 11 stars, and each star has an average mass of 2 times 10 to the power of 30 kilograms, calculate the total stellar mass. We are given the number of stars as 2 times 10 to the power of 11, and average stellar mass as 2 times 10 to the power of 30 kilograms. We need to find the total stellar mass. Step 1. Write the equation. We use total mass equals number of stars multiplied by average mass per star. Step 2. Substitute the values. We write total mass equals 2 times 10 to the power of 11 multiplied by 2 times 10 to the power of 30 kilograms. Step 3. Calculate. Using laws of indices, we multiply the coefficients. 2 times 2 equals 4. We add the powers. 11 plus 30 equals 41. Step 4. State the answer. The result is 4 times 10 to the power of 41 kilograms to 2 significant figures. Example 2 compares distances within our galaxy. The problem is, compare the Sun-Earth distance with the distance to the nearest star. The data shows Sun-Earth distance as 1.5 times 10 to the power of 8 kilometers, while the nearest star is 4 times 10 to the power of 13 kilometers away. Now we analyze. First, calculate the ratio of distances. We need to find how many times further the nearest star is compared to the Sun. Second, divide the distances. We calculate 4 times 10 to the power of 13 divided by 1.5 times 10 to the power of 8. Third, perform the calculation. 4 divided by 1.5 equals 2.7. 13 minus 8 equals 5. So we get 2.7 times 10 to the power of 5. Fourth, interpret the result. This means the nearest star is 270,000 times more distant than the Sun. The graph shows this enormous difference on a logarithmic scale, demonstrating the vast distances between stars in our galaxy. Mathematical skills are crucial for understanding galactic scales. Let's examine 3 key skills. First, scientific notation. When dealing with astronomical numbers, we use powers of 10. 200 billion is written as 2 times 10 to the power of 11. For multiplication, we multiply coefficients and add powers. 2 times 10 to the power of 11 multiplied by 3 times 10 to the power of 8 equals 6 times 10 to the power of 19. Second, order of magnitude comparisons. This means comparing the scale of different objects. A galaxy contains about 10 to the power of 11 stars, while our solar system has only 8 planets. This shows the enormous difference in scale. Third, distance units in astronomy. The light year equals 9.5 times 10 to the power of 12 kilometers. This is the distance light travels in 1 year at 300 million meters per second. These skills help us comprehend the vast scales involved in galactic astronomy. Now practice what you've learned with these 3 questions. Question 1 is basic level. It asks, state how many stars are typically found in a galaxy. This tests your knowledge of galactic scale and requires you to use scientific notation. Question 2 is intermediate. It states, explain why other stars in the Milky Way appear much fainter than the Sun. This requires you to apply the concept of distance and brightness relationship. Question 3 is advanced. The question is, calculate how many times more stars the Milky Way has compared to visible stars, which number about 3,000. This tests your mathematical skills with large number calculations. For all questions, remember to show you're working clearly, include units where appropriate, and check your answers make physical sense. Consider the enormous scales involved in galactic astronomy. Write your answers now before looking at the solutions. Physics principles about galaxies power our modern understanding of the universe. Let's see how today's concepts apply in practice. In space technology, the Hubble Space Telescope observes distant galaxies billions of light years away, helping scientists study how the universe evolved over cosmic time. The physics of stellar brightness and distance helps astronomers measure galactic properties. In navigation technology, global positioning system satellites use precise stellar positions as reference points for accurate location determination on Earth. The fixed positions of stars in our galaxy provide a stable coordinate system. In astrophysics research, galaxy studies reveal invisible dark matter and measure universe expansion through galactic motion analysis. These applications show why galactic physics matters. Career-wise, astronomy knowledge leads to many professions. Astrophysics research advances our understanding of cosmic structures, space engineering designs, telescopes and satellites. Satellite technology uses stellar navigation, and data science processes vast astronomical datasets. The concepts you learn today become tomorrow's space missions and discoveries. Let's review the solutions. For question 1, the answer is galaxies contain many billions of stars, typically 1 times 10 to the power of 11 to 1 times 10 to the power of 12 stars. This demonstrates the enormous scale of galactic structures. For question 2, other stars appear fainter because they are much further away than the Sun. The inverse square law means brightness decreases with distance squared, so vast stellar distances make other stars appear dim, despite being similar to our Sun. For question 3, we calculate 2 times 10 to the power of 11 divided by 3,000. Converting 3,000 to scientific notation gives 3 times 10 to the power of 3. Dividing gives 6.7 times 10 to the power of 7, meaning the Milky Way contains about 67 million times more stars than we can see. Now, exam success tips. First, always show you're working, especially for calculations involving scientific notation. Second, use scientific notation for all large astronomical numbers. Third, state comparisons clearly using precise language like much further or billions of times. Fourth, read questions carefully. State means give facts, while explain means provide reasons with scientific principles. Let's summarize today's lesson on galaxies. The key points to remember are, first, galaxy scale. Galaxies contain many billions of stars, typically 100 billion to 1 trillion stars, all held together by gravitational attraction. This represents the largest organized structures of matter in the universe. Second, the Milky Way is our home galaxy, a spiral structure containing about 200 billion stars, with our Sun located in an outer spiral arm, not at the galactic center. Third, stellar distances. Other stars in the Milky Way are much further from Earth than our Sun, typically hundreds of thousands of times more distant. These three concepts form the foundation for understanding cosmic scale and our place in the universe. For further study, review scientific notation techniques for handling large astronomical numbers. Practice making distance and scale comparisons using powers of 10. The next lesson covers the universe and Big Bang theory, which builds on today's work by explaining how galaxies formed and evolved. Ensure you understand galactic scales before exploring universal scales. Remember, astronomy builds systematically from solar system to galaxy to universe scales.